This is Math 204, and we're talking about section 3.2 now. This is derivatives and some more stuff about derivatives. So first up, a little lemma. Let f from the real numbers into the complex numbers be such that f of x is equal to ux plus iy. What am I doing wrong? Let's say ft xt plus iyt. There we go. Then the derivative is equal to, yeah, well, that makes sense, right? And in particular, existence of the derivative f dash t is equivalent to existence of the derivatives of x and y. Right, that's pretty simple. That just says that things work roughly the right way they do. It's important, however, the domain here is the real numbers, because we have this, which is interesting. If f goes from the real numbers to the real numbers, if f is a complex number and it maps into the real numbers, is such that f dash at a exists, then f dash of a equals 0. Woo! Yeah, this is a little weird. This is if the derivative of a function that takes complex numbers into real numbers is 0, then the derivative exists. If the derivative exists, then it has to be 0, which is a little different from this. But the proof of this is worth seeing, because it highlights a distinction between complex differentiation and real differentiation that I briefly mentioned in the previous, one of the previous lectures, or sections, talking about sections. So suppose f dash a exists, and then we have f dash a is equal to the limit as h goes to 0, f a plus h minus f a over h. And that's equivalent to saying, for all epsilon greater than 0, there exists a delta greater than 0, so that, and remember, h is complex. Yep, well, that's all fine. Okay, so now I'm going to have a look at this, calculate this from two different directions. In particular, suppose that h equals it, and t is in the real numbers, then it being less than delta is saying that f a plus it minus f a over it minus f dash of a is less than epsilon. So we're kind of fiddling a little bit with which portions of this are complex or not. Remember, that has to be real. So this is where we're going. Similarly, just a real number less than delta implies So in particular, the function f is real valued. So that's real, that's real. This is complex, that's real. Real, 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 real. Okay. So we know that the limit as t goes to 0 of fa plus it minus fa over it has to minus f dash of a has to equal the limit as t goes to 0 of fa plus t minus fa over t minus f dash a. Well, I can take off, cancel these bits, and both of these things have to be real. But this is clearly a complex thing. That's real, that's real, that's real. So this is complex. This thing over here, this limit, the value of this limit has to be in the pure imaginary things, and this thing over here has to be pure real. And this implies that f dash of a has to be an element of the pure reals intersect the reals inside the complex numbers, which implies that f dash of a has to equal 0. Pretty cool, I think. So an example. What if we had f of z is equal to the real part of z, which I'm just going to write down as x. dz of the real part of z is equal to 0. Or another way to put this is dz of x equals 0. Let's prove it. dz, the real part of z evaluated at a, is going to be equal to the limit as h goes to 0 of the real part of z plus h minus the real part of z over h, which is equal to the limit as h goes to 0 of x plus h minus x over h. And x's cancel, h's cancel, 1. But this is also equal to the limit as h goes to 0 of the real part of z plus I h minus e z over, say, IH. And this is equal to the limit as h goes to 0 of, well, that's x minus x over IH, which is equal to 0. Since these limits are different, the derivative doesn't actually exist. So neither of these things are true. dz, the real part of z, does not exist. Weird, right? Here's another example. dz of z evaluated at a, the limit as h goes to 0, z plus h minus z over h. Well, that's still 1. So dz of z equals 1. And in this particular case, it doesn't matter what you do with h. Just be careful. What goes wrong over here? Here I'm actually taking a little bit of a shortcut, because h could be complex or real. And so when I've gone from this step to here, I'm implicitly assuming that h is real. So this implicitly assumes, I didn't mention it at the time, apologies, h is real, which is why we get out this, and why we think about h being complex, we get out 0. So just be difference. Complex differentiation is a 2D kind of thing. Not a 1D thing. and real differentiation is a 1D kind of thing.